Algebra 2B students. How are you doing today? Today we're going to look at section 7.4, properties of logarithms. So in section 7.3, you learned about logarithms. They are the inverse expression or equations for exponential functions. And so today there's some properties of logarithms that are related to properties of exponential functions, of course, that we are going to look at. Notice today I actually had quite a bit of what you needed filled in because I really just want you to be able to understand instead of spending so much time writing. Notice also that there's a lot of details in the algebra, and I didn't want that to throw you if you put something small in the wrong place. So let's begin. We're going to use properties of logarithms, those are called logs, to simplify logarithmic expressions. So there is a product property of logarithms, and this says in words the log of a product. That means that you multiply, is what product means, if you remember, is equal to the sum of the logs of actually adding up the logs. Let's take a look at the algebra that goes with that. Let's say that you have log base b of one number or expression times another. What you can do, what an equivalent expression is we can take the two terms that are being multiplied and break them into two logs with a plus sign between. So if you have log base b of m times n, that is equal to log base b of m plus log base b of n. Now, please remember that logs are really just exponents, so the reason why this is true, you knew that a base to the m power times a base to the n power meant that you kept the base and added the exponents. And so that's what the logarithms say. They're saying that when the base is b and you have a multiplication, that you can add the exponents. Logs are exponents. So let's go in the middle here and let's do an example. Let's say you have log base 2 of 2 times 4. That is equal to, by the product property, log base 2 of 2 plus log base 2 of 4. So this expression is the same as the one above. Now let's take a look at what these expressions actually equal. Log base 2 of 2 times 4. Let's go ahead and simplify that. That would be log base 2 of 8. So if I asked you, when the base is 2, what is the exponent that produces an 8, you would tell me 3. On our second expression, log base 2 of 2, that says when the base is 2, what is the exponent that produces a 2? That is a 1 plus log base 2 of 4. So a base of 2, what is the exponent that gets you 4 is 2. And notice 1 plus 2 is equal to 3. So these are both equal to each other. Let's take a look at the quotient property of logarithms, number 2. That says that the log of a quotient, which means division, is equal to subtraction of the logs. Let's go over to the algebra. If you have a log with a base of b, and your solution, your expression, has two terms being divided, you can also write it as two separate logs with the same base with a subtraction between the logs. Log base b of m minus log base b of n. Again, this is because you knew when bases were the same and they were being divided that you can subtract the exponents. Let's do an example with numbers in the middle. If you have log base 3 of, let's do 27 divided by 3. You could write that, we call it expanding that, as log base 3 of 27 minus log base 3 of 3. And that would be an equal expression. Why do we want to split up logs? Because sometimes each log is simpler than the original and we can solve it better. So let's take a look at the first problem. Let's clean it up a little. Log base 3 of 27 divided by 3. Well, 27 divided by 3 is 9. So log base 3 of 9 equals. So when the base is 3, what is the exponent that produces a 9? That would be 2. So we should get the same answer here with the subtraction because it's equivalent. Log base 3 of 27 is 3 to what exponent is 27 is 3 minus log base 3 of 3. 3 to what exponent is 3 is 1. 3 minus 1 is 2. They are equal to each other. Let's look at the power property of logarithms. The words say the log of a power is equal to the product, remember that's multiplying, of the exponent and the log. So, in other words, I know this is kind of in the corner of the video. If you have a log base b and your solution has its own exponent on it, that means that you can bring that exponent out front and multiply it by the rest of the log. These two expressions are equal. And again, that's because a log is an exponent, and we know when you had a base with an exponent raised to another exponent that you multiplied those exponents, Let's try some numbers. Let's say that you have, let's do log base 5 of 25 squared. Notice that I have a base of 5, I'm asking for an exponent, and the solution is 25 squared. Using the power property, that is equal to bringing the exponent of 2 out front and multiplying it by the rest of the log. Let's see if these two expressions are equivalent. Let's take a look. Well, this one we might need a calculator for, right? 25 squared. I'm not even sure. I think that's 625. I forgot my calculator. Sorry, it's been a long day, students. So, 25 squared. Hey, at least I was right. It's 625. Okay. Now, let's see how many times we have to multiply 5 to get 625. 5 times 5 is 25. Times 5 is 125. Times 5 is 625. The exponent is 4. Now let's take a look here. 2 times log base 5 of 25 should be the same. Let's do the log first. When the base is 5, what is the exponent that produces a 25? That would be a 2. Multiplied by the 2 out front, and we get a 4. Notice that these answers are both the same because the properties are true. Let's go to the next page. All right, on the next page, it looks a little bit more complicated, but I promise you that it turns out pretty easy. Because logs and bases and exponential expressions are inverses of each other, if you have a log of a base and you have that same base to an exponent, then these two, the log and the exponent base, cancel each other out and just leave the exponent. So an example of that would be, it might look complicated, but if you had log base 2 of 2 cubed. Now you are welcome to throw this in the calculator and evaluate it, but what you would find is the log base 2 cancels out the base of 2 of the exponential expression, again because they are inverses, and leaves the exponent. It also works the other way around, where instead of starting with a log and then having an exponential expression, if you start with an exponential expression that has a log. So base b of log base b of x, the base cancels out the log base and still leaves the x. So let's turn that around. Let's say that you have a base of 5 and log base 5 of let's use 6. The base of 5 and the log base of 5 cancels out and does leave a 6. So even though it looks complicated, it's very usable. Number 5, let's look at the change of base formula. We used to need this a lot more before we had log base on our calculator. So this is really just kind of for your information, but you may come across some problems that use the log base. So here's what I want you to know. If you have log base b of x, you can change the base. Notice we changed the base to a. That would be really useful if that a was a 10, because we have log base 10 on our calculator. Very useful. I'll do an example. That you can rewrite it as log base a of the solution divided by log base a of the base. So let's take a look. This would be, let's say you have log base 5 of 16. This would be hard for you to figure out on your own. This is not a nice integer answer. What you could do is on your calculator, let's use our base of 10 because it's on the calculator. You could do log of the solution divided by log of your original base of 5. And in the calculator, you would get the same answer. Let's go ahead and do that. Log base 5 of 16. Log base, if you remember, is on your math button, going down to log base. There it is. Base of 5 in my original problem of 16. Let's round that. 1.723. 1.723. Now on our calculator, let's do log of 16 divided by log of 5. Okay. Notice because a base is not showing, we're using base of 10, which is on the left of your calculator. I think I'll use a numerator denominator, an ND, so you can see the whole thing. Log of 16 divided by log of 5. Notice we get the same answer, 1.723. Again, this change of base formula is not quite as useful now that you have log base on your calculator, but I wanted you to see it. Let's do some examples of the product property and quotient property. Let's take a look here. Complete the steps on number 1 to simplify each expression. Notice you have log base 6 of 54 plus log base 6 of 4. Because I see that the bases of 6 are the same, they always will be, and there's a plus sign in between, that means I can use the product property at the top of the page. I can write 1 log with the 54 multiplying the 4. And 54 times 4 is 216. So I have log base 6 of 216. Let's throw that in the calculator. Let's use our log base and get a final answer. Log base 6 of 216. That is a really nice 3. Let's just check that mentally. If you have a base of 6, 6 times 6 is 36, times 6 is 216. With a base of 6, that is an exponent of 3. Let's look at the next expression. log base 2 of 128 minus log base 2 of 8. Notice because you have a minus sign, that would be the quotient property. So I can write this expression as 1 log base 2 with the first term divided by the second. Now let's go ahead and see what is log base 2 of 128 divided by 8. Let's see, we can use our calculator, but let's see, 8 goes into 12 once, that leaves a 4. That is log base 2 of 16. You are welcome to throw that in the calculator, but I can work that out myself. With a base of 2, what's the exponent that gets me 16? That would be a 4. Next, number 3. Log base 9 of 3 plus log base 9 of 27. I see a plus sign. This will be the product property. Log base 9, and I will multiply the 3 by the 27. There we go. And let's keep doing that. Let's continue 3 times 27. That would be log base 9 of 81. And again, you can put this on the calculator, but log base 9 of 81, when the base is 9, what's the exponent that produces a solution of 81? That would be a 2. Last page. Let's use some of the, we're going to use the power property and some of the inverse properties that, again, look a little complicated but are super easy. So let's complete this last page. We have log base 5 of 125 squared. Anytime you see an exponent on a solution, that is the pattern we're looking for that tells us to use the power property. It says we can bring the exponent out front, the 2, and multiply it by the rest of the expression, by the rest of the log. And that can help us solve it. So let's take a look. Let's keep our 2, log base 5 of 125. So when the base is 5, what is the exponent that produces 125? That would be a 3, and 2 times 3 is 6. Notice I was able to do this problem mentally, where above, I could not do 125 squared mentally. Number 5, log base 2 of 16 to the 4th. We bring that 4 out front, multiply it by the rest of the log. Again, 16 to the 4th I can't do mentally, but this problem I can. This would be 4 times, and log base 2 of 16 is 4. And 4 times 4 is 16. Log base 9 of 81 cubed. Let's bring that exponent out front, multiply it by the rest of the expression. Here's my 3. When the exponent is 9, what is the exponent that produces 81? That is a 2. My final answer is 6. Now to wrap this up, we are going to look at inverse properties of logarithms. Take a look on number 7. You have a log with a base of 6 and an exponential expression with a base of 6. The log base 6 and the base of 6 cancel out, leaving you with a 5y. Isn't that great? Looks super complicated, so easy. When you have a base of 4 and in the exponential expression you have log base of 4, the base of 4 and log base of 4 cancel, you are left with a 75. Last one, base of 2, and in the exponent you have log base 2 of 3x. Cancel, and write what's left. There you go. Thanks for hanging out with me today, students. And that is it for section 7-4.